So we worked this problem previously. We have a series RLC circuit, and when we did it before, we started by finding the voltage, and then we took the derivative to find the current. So we were looking for the current through the capacitor, and so I said that's what we were going to do. And then I wrote down that we were going to find the voltage across the capacitor. And I proceeded to solve for the voltage, and then was surprised that I got an equation for the voltage instead of the current. So I'll do it this time. We'll actually find the current. So here's our general solution. So x of t is going to be IC of t. Now notice that the current through the capacitor is going to be the same as the current through the inductor because they're in series. Okay, so it's in series, so alpha equals R over 2L. And we previously had found that, and you just plug it in. We've got the resistance and the inductor. We had found that to be 2800. And then omega naught is 1 over the square root of LC. And we had found that earlier to be 10,000. And alpha is less than omega naught, so we knew it was underdamped. So for underdamped, we have this equation, and we will need omega d. So omega d is the square root of omega naught squared minus alpha squared, which earlier we had found to be 9600. All right, so we need to find D1 and D2. So D1, our function here is current through the capacitor. So this will be IC of 0 minus IC at infinity. And we, okay, so we'll do that. So at 0, well, we also had previously found, we had looked at our circuit, and we know that the capacitor was originally charged. So V of 0 was 100. And we knew V, this is VC, and we knew VC at infinity was going to be 0. There are no power sources. And we knew IL of 0 minus was 0. And then because current can't change instantaneously through an inductor, IL of 0 is also 0. So at 0, when we have the switch action, our capacitor and inductor are in series, so they have to have the same current. And so IC of 0 has to equal IL of 0, which has to equal 0. So we know IC of 0 is 0. And we know IC of infinity, so the capacitor is going to completely discharge. All the energy will be dissipated through the resistor, so IC at infinity will be 0. Okay, so now we need to have IC prime of 0. Okay, so let's think about something that has a di dt in it. Well, we know that VL of t equals L di dt. So that will get us, well, again, so this is dIL dt, but we are in series. So dIL dt will be the same as DIC dt. So VL, and we want it at 0, VL at 0 is going to equal L times IC prime at 0. But now we need to figure out the voltage across the inductor at 0. Now, voltage can change instantaneously on an inductor. So let's take a look at our circuit. We knew VC of 0 was 100. And so that's VC of 0 minus was 100, which means VC of 0 plus is 100. So we have, so this is 100. And now let's use KVL to figure out the voltage across the inductor. Okay, so we know that the voltage across the capacitor is 100. Our current is 0, so there's no voltage change from the resistor. So then plus the voltage across the inductor has to equal 0, or VL of 0 equals negative 100. So negative 100 equals L, which was 100 millihenries, IC prime of 0, or IC prime of 0 equals negative 1000. So we've got that. Oh, I never did find D1. Okay, so D1 is IC of 0 minus IC at infinity. Which was 0 minus 0, which was 0. D2 is X prime of 0, IC prime of 0, plus alpha times IC of 0 minus IC at infinity over omega D. So D2 equals minus 1000 plus alpha times 0 over 9600 or D2 is minus 0.104. And so now we have everything we need to plug into our equation. We have IC of t equals e to the minus alpha t times d1 cosine omega dt plus d2 sine omega dt plus IC at infinity. So this will be e to the minus, and what was alpha? Alpha was 2800, e to the minus 2800 t, and d1 was 0, and d2 is minus 0.104 sine, and omega d is 9600 t, plus IC at infinity was 0, and so our current is minus 0.104 e to minus 2800 t sine 9600 t, which is what we expected to get, and which I did this before when I took the derivative and I got that tiny little insignificant part that had the cosine in it that was so small that must have been due to rounding error.